Okay, good morning, everyone. Here's a bit of a mess, but we're not gonna worry about that. I don't know why it's kind of lopsided. It's ridiculous. Anyway, we don't care about that. The goal for today. Actually, I do care about that, low key. I'm not gonna hold you. Oh, never mind. So the goal for that is to. Sorry, the goal for today is to finish the nature catalysis paper that I was reading earlier. Now, it is not an open access paper, so I can't really narrate as much as possible. But if you join in and you just want to study along, listen to some chill ambient music, feel free. Feel free. It's the goal here is to study and study effectively, right? So, yes, let us begin. So, what do we have so far? Oh yeah, I have something on the stove. Let me go turn it off. Mm, let me see. Do I understand this right? Um, so current strategies for carbon-carbon bond activation across two heteroatoms involves four category strategies that can be categorized by atom economy principles. The fourth, which is the fourth one, which is the focus of this paper, is carbon-carbon bond involving substrates. Right. So substrates that um, so I think what they're saying is among, like, yes, there are like three other systems, but the fourth one that is most important to them is the use of substrates that specifically cleave carbon-carbon bonds, aka metals. Right. So from both a synthetic and medicinal chemistry perspective, type 4 substrates offer practical advantages by preserving functional group integrity in ring homologs. Okay. Let's see. However, the inherent challenges of carbon-carbon bond activation, ubiquitous presence in. Okay, so thing to know. Have necessitated strategic substrate engineering. Current successes predominantly use carbon-carbon bonds alpha to one heteroatom. Mm-hmm. So what do they mean? Current successes predominantly use. So what do we mean by use carbon bonds alpha to one heteroatom? Figure 1CI. Carbon bonds. So are we talking about annulation? What is the annulation is the process of building a new ring structure. Oh, okay, okay, so okay. All right. Annulation. Okay, so now bringing everything into context, right? Important efforts have been devoted over the past several decades to develop alternative annulations, which is the process of several processes have been developed to develop have several processes have been developed to build to the building of new ring structures, and these strategies can be categorized across four atom economy principles. So the focus of this paper is ring formation using um, the Diels-Alder system, and I think what I'm getting from it is that the at some point in the ring formation from a beta lactam, you would need to do some carbon-carbon cleavage, right? So at some point in the annulation of a beta lactam, you need to do some carbon-carbon cleavage. But the difficulty with doing carbon-carbon cleavage is that if the carbons have heteroatoms on them, then the bonds between the carbons and the heteroatoms themselves are competing for cleavage with the, but we're also competing with cleavage from the substrate, right? So putting things into perspective, it seems that what this paper is trying to say is that, hey, we have developed a method to help solve that specific okay, I want to call it a race condition because generally that's what it sounds like, right? To solve that race condition between carbon heteroatom bonds and carbon carbon bonds. During the annulation of a beta lactam, right? Okay, so let's read. Let me just read this thing again. The Diels-Alder reaction between dienes and dienophiles stands as a cornerstone methodology for six-membered ring construction. All right, six-membered ring construction. Let's highlight that. Can I hide? Wait, why can I hide? Okay. Building upon this paradigm, important efforts have been devoted over the past several decades to developing alternative annulations using non-diene precursors. Okay, so focus annulation non-diene precursors. Diels-Alder reaction between dienes and dienophiles stands as a cornerstone methodology for six-membered ring construction. So the fact that we're putting that into perspective first, it kind of seems like it's trying to make another method for six-membered ring construction. Okay, so building upon this paradigm, important efforts have been devoted over the past several decades to develop an alternative annulation. So, an alternative to Diels-Alder reactions has been is being has is still being researched for the past. So, alternatives for Diels-Alder reactions have been in the research pipeline for more than several decades. For several decades, right? And this is because when you have alternates to the Diels-Alder reactions, you can expand substrate scope and enhance molecular complexity instead of just using a dienophile. Okay, so I think I see the picture now. Okay, so hence current strategies can be systematically categorized. Current strategies can be systematically categorized by atomic economy principles. Type 4. So current alternate strategies can be categorized according to four principles. Where the fourth one, um, carbon-carbon bond involving substrates. So to put that in perspective, right? We are trying to find alternatives for Diels-Alder ring formation paradigms, and alternatives have been researched for the last over the past several decades, and the specific focus on in this paper are methods that involve carbon-carbon bond involving substrates. And like, well, what do they mean by that? No. The fourth method uses carbon-carbon bond involving substrates that deliver the All right. Okay. We're getting somewhere. We're actually getting somewhere. All right. However, the inherent challenges of so Tafford substrates offer practical advantages by preserving functional group integrity in ring homologs and avoiding more sacrificial molecular fragments and streamlining lead compound optimization. However, the inherent challenges of carbon bond activation ubiquitous however, the inherent challenges of carbon-carbon bond activation, ubiquitous presence in organic frameworks and low transition metal affinity. So, what do they mean by that? The ubiquitous presence in organic frameworks and low transition metal affinity. Are they saying these organic frameworks that that generate substrates that involve carbon? What do they mean? So I mean, we're still gonna listen to this. Yes, sir. Okay, give me a second. I gotta. My bad. I had to go grab breakfast amongst other things. All right. I just have like a bowl of yogurt with some honey in it. I had some milk earlier with some creatine, and this is 8% fat, like yogurt, by the way. Ugh. Okay, so let's see. Right, so the fourth method, which is an expansion of current deals all the alternatives for ring annulation, uses substrates that involve carbon-carbon bond activation. That's where we are right now. Okay. So current, and what it's saying is the challenges of carbon-carbon bond activation have necessitated strategic substrate engineering. Right. So, I think. I mean, it has to be. Okay, substrate engineering, the thing that gets reacted on. Okay, it's so funny because like for some reason I was there, like I thought the substrate was the one doing the carbon-carbon bond activation. Well, I think it is. It's just that like basically let's continue. However, the inherent challenges of carbon-carbon bond activation, ubiquitous, which is I hate the way they hyphenated this thing. However, the inherent challenges of carbon-carbon bond activation, ubiquitous presence in organic frameworks and low transition metal affinity. What does this even mean? Why is this in hyphens here? Oh my gosh, I wish I could show you guys. Okay. Have necessitated strategic substrate engineering. Okay, let's continue. Current successes predominantly use carbon-carbon bonds alpha to 1 heteroatom. Right, so engineering the substrate. of annulations by carbon-carbon bond activation. Okay, so previously we used Diels-Alder. Now we are using carbon-carbon bond activation. This dienophile here. Let's see. All right, let's see. Uses. Are they saying that with type 4 they make them? Because if I'm to go with this image here, what I'm basically getting is that, so this is a four membered carbon structure, right? And essentially what I'm getting here is that with type 4, say it was a butyl group, right, that you wanted to use for the bond activation, that you wanted to like make a six-member ring with. Oh my, okay. It's so stupid. Okay, it's not stupid. I think I understand it now. The end goal here is to make a six-membered ring. All right, so keeping that in mind, if the end goal is to make a six-membered ring, we are then free to engineer the substrates to work better with type 4 strategies, right? Because since it's not really the engineering of the substrates that is a goal, but the formation of the six-membered ring ultimately, right? Okay, I think I get it. It's not the goal, but the which makes sense when you then frame it as. I mean, obviously that's what it's been framed as. I just was too slow to pick it up. But since the formation of six-membered rings is the end goal, we are free to engineer the substrate, right? So instead, you can use like a butyl or can use cyclobutyl if it's gonna preserve some atoms or things like that. Including cyclobutanone derivatives. Including cyclobutanone derivatives, cyclopentanone, cyclobutanols, cycloalkylamines, cyclopropane, carboxylate/vinyl derivatives. Okay. So these systems circumvent site selectivity challenges through symmetrical functional group placements. Nevertheless, the activation of carbon-carbon bonds alpha the two hetero atoms in privileged heterocycles For example, lactams and lactones. Remain in our soil frontier. Alright, so the problem. Carbon compound activation. Carbon compound activation. Of CC. So actually, hold on. So the problem activation of CC bonds. Activation of CC bonds. Alpha. So two heteroatoms, i.e. CC, then like NH2 and OH. It's hard. Okay, so it's this is so it's weird how scoped in this thing is, right? Because it's like what they're essentially trying to say is back in the day. Okay, well, not back in the day. So the classic way to make a six-membered ring would be to use a Diels-Alder paradigm, right? It's like a cycloaddition of a diene and another like dienophile, right? So it's like you have your two, like you have your 1,3 butte buttes. No, you have your you have like I say 1,3 butte 1,3 diene plus what you call it? Gosh, ethene in the cycloaddition to give you like a six-membered ring, right? What essentially they're saying is that there have been several efforts. Yeah, there have been research efforts to expand that paradigm to use dienophile reagents, right? So that way you can enhance like the molecular complexity of this like system, and in doing so, on all the research efforts so far, you can broadly categorize them into four atom economies, which I'm yet to fully understand, right? But along those four atom economies, one is the usage of carbon-carbon involving substrates, which from the image, which based on the image I've seen here, is the usage of cyclic butyl compounds, right? And again, the best part about this is it preserves the functional group integrity. It doesn't. There's zero atom loss with this system. It preserves the functional group integrity. All right. However, when the region in a cyclic in a heterocycle, so I think the problem now is that even though this works, and yes, you don't lose atoms, and yes, you preserve the functional group integrity, if you then try to activate the carbon-carbon bonds, and each of these carbon-carbon bonds have a heteroatom, right? Your metal, because that's what they're using here, that you would use in cleaving this system, these bonds, will be in the race condition with the carbon-carbon bonds and the carbon heteroatom bonds on both atoms, right? So it's an unsolved frontier, which I guess this is where the nickel aluminum bimetallic catalysis comes into play. That's my understanding. It's competitive and it's a race condition. Adjusting this limitation will report a phosphine oxide ligating nickel aluminum bimetallic catalytic system that achieves C2C3 bond activation in the beta lactams, overriding the intrinsic reactivity of the neighboring N1C2 bond. And now, what is a beta lactam? Beta lactam structure. Beta lactam is a 4-member cyclic amide. Okay, so heteroatom here, heteroatom here, and then we. Okay. So a beta lactam. So they demonstrated the system on an actual. Okay. But wait. But how? Okay, I mean, whatever. We'll see. Let me see. Is this it? I thought it was gonna be more like. I mean, it is cyclic, and the carbon here has the. Anyway, okay, it's okay. Well, we're gonna see the image. So I mean, I guess in this case, carbon and nitrogen can switch, and now instead of carbon bond activation, it's carbon nitrogen bond activation. But I don't get how it works in beta lactams though. Right, because like this is a beta lactam. Here's my thing right here. So this is a beta lactam. Let me see. This is a beta lactam, right? So you have your. I'm gonna draw the line here. So you have like this, then obviously you have your N here, nitrogen. This is nitrogen, by the way. And then I'm just gonna continue drawing this whole thing. You have this guy, this obviously has a hydrogen on it, and then there's like a oxygen here, and there's a hydrogen here. So this is a beta lactam, right? So my thing is, if I thought it was carbon-carbon bond activation, because which carbon-carbon bond are we targeting? Oh, unless wait, what? Unless, okay, so unless what they meant was that instead of the race condition doesn't happen like between. I mean, it could possibly happen when one amino group is here and one amino group is here, but it could also happen when both heteroatoms are on a single carbon atom. Okay, I mean, I guess that makes. I guess that would make sense. Whew. All right. 7:33, 7:45 needs to be done. All right. So I think we've I think I understand it now. Because when I look, I mean, I can't really show you guys, but like looking at this paper here, nickel ligand, aluminum methyl ligand, and then they form this, right? And it also, and I see what they say by it. It's this carbon they're activating. But it doesn't. Wait. So did I not read this right? Like I thought it said it's carbon-carbon bond activation, right? So, and Nevertheless, the activation of carbon-carbon bonds, alpha to two heteroatoms in privileged heterocycles, for example, lactons and lactones, remains an unsolved frontier. The key obstacle stems from competitive activation of adjacent carbon X bonds, where X is either nitrogen or oxygen or sulfur, which dominate over carbon-carbon bond cleavage. But where did they say two heteroatoms, right? So give me a second. Did I not? Okay, I mean whatever. So, let me see. 7:35. All right, we're gonna be like literally crunch time right now. Oh fuck! I got broccoli on the stove. We got 5 more minutes, and I just got done meal prepping. All right, it's okay. It's okay. Yeah. Surface scope with alkynes. I substitute with alkenes. Having established a catalytic system's efficiency with alkynes, next explores compatibility with alkenes, a class traditionally challenging for carbon-carbon insertion due to beta hydrogen elimination. Alright, so I think how I'm going to structure this is that, in an effort to diversify annulation strategies, the goal of this paper was to demonstrate a new system for a class of annulation strategies. It was to demonstrate a new system for carbon-carbon activation in a class of in a class of annulation strategies on beta lactams. And I'm just gonna skim over this like dead ass. I'm gonna skim over this real quick. Okay. Substrate scope with alkenes. Having established catalytic systems efficiency with alkynes, we next explored its compatibility with alkenes, a class traditionally challenging for carbon-carbon insertion due to beta hydrogen elimination. Beta hydrogen, yeah, whatever, okay, cool. Due to quick beta hydrogen elimination of organometallic intermediates, the intermolecular insertion of inactive alkenes into carbon-carbon bonds has been a major challenge. Okay, so due to beta alright, so beta hydrogen elimination makes it difficult. Alright, so let's see. Here's your cyclic beta lactam. If your R group here, try to activate this carbon-carbon bond. Let's see. Reaction conditions: beta lactam, 0.2 moles, alkene, toluene, aluminum, butyl. Gratifyingly addressing the challenge of beta hydrogen. So gratifyingly addressing the challenge of beta hydrogen elimination and alkene insertion, sterically hindered PO10 ligand enabled efficient reactions. Norbornene derivatives. Who is naming these things, bro? Like norbornene. You know, like what happened to IUPAC? Like why can't we just use the IUPAC, bro? Like use the IUPAC. Norbornene. Like I can't even imagine that in my head. I guess I just need to study more. I guess I just need to study more. Achieve near quantitative yields. Why styrenes afforded beta gamma lactams with. Alright, it worked. Synthetic applications. Annulation demonstrated excellent scalability. Reacting with beta lactam S1. Blah 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 blah. So it works. Obviously, to elucidate the mechanism of an annulation reaction, a series of mechanistic experiments were performed. Although crystallization of the complexes was unsuccessful, a single crystal of analogous PO1 nickel aluminum was obtained and characterized by H1C13 and P31 NMR. While PO1 nickel aluminum insertion was inert in the annulation reaction, addition of an equimolar amount of aluminum methyl activated the species and enabled the transformation, affording the product in a yield comparable to that under standard protocol. This result indicates that PO1 nickel aluminum complex serves as a precursor. Okay, got 1 more minute. Precursor to the active catalytic species. Alright, boom, bada bing, bada bang. Nice. Conclusion, reference. Alright, nice, awesome paper. Love what you're doing with the lactams, with the beta lactams. It's cool. So I mean, if I were to summarize this, I think like the takeaway is that in an effort to in an effort to diversify annulation paradigms, and by paradigms, it's literally just Diels-Alder, right? Several strategies have emerged over the last several decades, and you kind of classify them into 4 different atom economies. The 4th one, which uses a carbon-carbon bond substrate that results in no atom loss and also stores and preserves the functional group integrity of the ring that it forms, right? However, the problem with that system is that activation of a carbon-carbon bond that happens to have a hetero atom was difficult because it led to race condition whereby your substrate no, well, your enzyme or compound, your cleavage compound is trying to what do you call it? It's competing. It's trying to cleave the. Let me take that back. The problem was that when you have heteroatoms on a on a carbon that you want to activate on a carbon compound you want to activate, the activation like you're not just like in that sense the bonds between the carbon and the heteroatom are also competing for cleavage with a carbon-carbon bond, so it becomes difficult, and it's especially difficult when well, not especially difficult. I'll just shut up on that. So what this guy what they did was to use the nickel aluminum. I need to probably just refresh on the nickel aluminum complex that they created, and basically developed a system that just that works on beta lactams. So far, they haven't done it on other. I mean, I haven't seen them do it on other what you call cyclic compounds, right? What did they? I think they did. Oh shit, they did. Huh. Okay. Yeah, they did, and it worked. Yeah. So that's kind of the summary of the paper, rough summary. Skim through a lot of things here, but it's okay. All right, I'm gonna stop streaming. I need to get ready to go to work. Au revoir. Love you guys.